Hello, my name is Kevin Craig. I have created 12 modules on electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used throughout the world to represent the field known as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This is Module 9 on diodes. Topics include an introduction to insulators, conductors, and semiconductors, the p-n junction, the signal diode, the power diode and rectifier, half-wave rectifier, full-wave rectifier, and bridge rectifier, the Zener diode, the Schottky diode, and the light-emitting diode. An introduction to diodes. If the resistor is the most basic passive electrical component, the diode is the most basic active electrical component. However, while resistor behavior is linear described by Ohm's law, diode behavior is nonlinear, described by a nonlinear voltage-current relationship. Diodes are basic unidirectional semiconductor devices that will only allow current to flow through them in one direction, acting more like a one-way electrical valve. Diodes are made from a single piece of semiconductor material which has a positive P region at one end and a negative N region at the other, and which has a resistivity value somewhere between that of a conductor and an insulator. Here is a table showing the resistivity of conductors, semiconductors, and insulators. In a conductor, electrons migrate freely when an electric field is applied. In an insulator, electrons do not move easily when an electric field is applied. And a semiconductor has properties somewhere between conductors and insulators. This chart shows the values of resistivity, represented by the Greek letter rho, with units of ohms, meter. This is a material property. We see materials like silver, gold, and carbon have very low values of resistivity. Insulators like glass and quartz have very high values of resistivity. And semiconductors like germanium and silicon are in the middle. Resistor, or resistance, is defined as the voltage across an element divided by the current flowing through an element. And the resistance of a piece of material is defined as the material property resistivity rho times the length of the material divided by the cross-sectional area of the material. Resistivity is the reciprocal of sigma, which is defined as conductivity. And resistivity of conductors is not a constant, but will increase as temperature increases. The diagram shows the valence and conduction bands of insulators, metals, and semiconductors. The valence band is the outermost band electrons occupy in a particular atom. the energy difference between the highest occupied energy state of the valence band and the lowest unoccupied state of the conduction band is called the band gap, and is an indicative of the electrical conductivity of a material. A large band gap means that a lot of energy is required to excite valence electrons to the conduction band. Conversely, when the valence band and conduction band overlap, as they do in metals, electrons can readily jump between the two bands, meaning the material is highly conductive. And we see the semiconductor is in between the metal and the insulator in this diagram, showing the valence band and conduction band and the band gap. In a semiconductor crystal, a valence electron can jump to the conduction band and leave a hole in the valence band, which can be filled by a valence electron from a nearby atom. Current can be thought of as the movement of holes in one direction or electrons in the other. Properties of pure semiconductor crystals can be changed by doping. That is, adding small amounts by either diffusion or implantation of elements called dopants from group 3 of the periodic table, boron or gallium, or group 5 of the periodic table, arsenic or phosphorus. Group 5 dopants are called donors because they enhance the electron conductivity of the semiconductor, resulting in an N-type semiconductor. Group 3 dopants are called acceptors because they cause the formation of holes, which are positive charge carriers in the semiconductor, resulting in a P-type semiconductor. The purpose of doping a semiconductor, therefore, is to elevate and control the number of charge carriers in the semiconductor. In an N-type semiconductor, the charge carriers are electrons. In a P-type semiconductor, the charge carriers are holes. The interaction between N-type and P-type semiconductor materials is the basis for most semiconductor electronic devices. Contemporary electronic devices are produced by creating microscopic interfaces between differently doped semiconductor material. Here is the periodic table of the elements. We want to focus on group 3, group 4, and group 5. Let's look more closely at this portion of the periodic table. Here is the portion of the periodic table we want to focus on: group 3, group 4, and group 5. Group 4 are the semiconductor materials silicon and germanium. The group 4 elements have 4 electrons in the outer shell. The group 5 elements used for doping are phosphorus, arsenic, and antimony. The most commonly used material is antimony. The group 5 materials have 5 electrons in the outer shell. When they dope a semiconductor material, they enhance electron movement and create an N-type semiconductor. The group 3 materials have 3 electrons in the outer shell. They are boron, aluminum, and gallium. The most commonly used doping material from group 3 is boron. When they are used for doping a semiconductor material, they create a P-type semiconductor as hole movement is enhanced. This diagram shows the silicon atom structure. Silicon is a group 4 material. It has atomic number 14, and it has 4 electrons in its outer valence shell. And we see the shared electrons among the silicon atoms. Antimony is a group 5 material. Atomic number 51, it has 5 electrons in its outer shell, and it donates electrons to the silicon atoms, thus producing a free electron. It enhances electron movement and creates what we call an N-type semiconductor. Boron is a group 3 material. Atomic number 5, it has 3 electrons in its outer valence shell. When it's used for doping, it creates a p-type semiconductor as it shares electrons with the silicon atoms and results in a hole. Conduction is by hole movement. A p-n junction is formed when a n-type material is fused together with a p-type material, creating a semiconductor diode. The charge transfer of electrons and holes across the p-n junction is known as diffusion. Here in the n region, we see free electrons. In the p region, we see holes. Across the depletion layer, there is a potential difference across this junction, as shown by this diagram. This diagram shows the p-n junction in equilibrium, where the depletion layer is in equilibrium, satisfying the relationship that the concentration N of donors times the width of this donor region is equal to the concentration of acceptors times the width of this acceptor region. There are 3 possible biasing conditions for the standard p-n junction diode. Zero bias, no external voltage potential is applied to the p-n junction diode. Reverse bias, the voltage potential is connected negative to the p-type material and positive to the n-type material across the diode, which has the effect of increasing the p-n junction diode width. Forward bias, the voltage potential is connected positive to the p-type material and negative to the n-type material across the diode, which has the effect of decreasing the p-n junction diode width. The graph shows the p-n junction diode voltage current characteristics. The p-type material is called the anode. The n-type material is called the cathode. The conventional current flow is from the anode to the cathode. Here is the symbol for the diode. The current flows in the direction of the arrow. No current flows opposite to that, as shown by the vertical line that blocks current flow. Here is a graph of current versus voltage. If we have a positive voltage applied from the anode to the cathode, we see the current flow in the p-n junction diode. Initially, the current at low voltage, low forward voltage, is very small, and then at the knee, which is 0.3 volts for germanium, 0.7 volts for silicon, we get significant current flow. In the opposite direction, when we have reverse bias, we see that there is no current flow until we get to a very high voltage, which is called the reverse breakdown voltage. And then the current, the reverse current, increases dramatically. And we call this Zener breakdown. For germanium, this current flow when it is reverse biased is very small, minus 50 milliamps for germanium, minus 20 milliamps for silicon. So this shows the PN junction diode voltage current characteristics, both for forward voltage and reverse voltage. Here is the PN junction when we have zero bias. No voltage is applied across the PN junction. Here is a circuit with a resistor and our diode in the circuit. There's a built-in potential of 0.3 to 0.7 volts across the PN junction. When the diode is reverse biased, as we see, here is the battery, the positive connected to the N region, the negative connected to the P region. We see that the electrons move to the far left, the holes move to the far right, and the depletion layer gets wider. No current flows. As we see here, when the battery is connected as shown, no current will flow, and the diode behaves like an open circuit. In the reverse bias region, we see the magnitude of the current that will flow. Up until almost 80 volts, the current is in the nanoampere range. And then at some large negative voltage, we get a reverse breakdown and we get reverse current that is much greater. When the diode is forward biased, the positive side of the battery is connected to the P region, the negative side is connected to the N region. We see the negative charge carriers go from the N region to the P region. Positive charge carriers go from the P region to the N region. And we have current flow. The depletion layer gets very, very small. When the battery is connected as such, positive to the anode, negative to the cathode, current flows through the diode in the direction of the arrow and then through the resistor. The diode behaves ideally like a short circuit. In the forward bias region for a silicon diode, when voltage is applied, very little current flows until the voltage gets to be about 0.7 volts, at which point significant current will start to flow. That represents the knee of this forward bias region. And we see the values of the forward current in this forward bias region. PN junction region of a junction diode has the following important characteristics. Semiconductors contain two types of mobile charge carriers, holes and electrons. The holes are positively charged, while the electrons are negatively charged. A semiconductor may be doped with donor impurities such as antimony, which is N-type doping, so that it contains mobile charges, which are primarily electrons. A semiconductor may be doped with acceptor impurities such as boron, or P-type doping, so that it contains mobile charges, which are mainly holes. The junction region itself has no charge carriers and is known as the depletion region. The junction, which is the depletion region, has a physical thickness that varies with the applied voltage. When a diode is zero biased, no external energy source is applied, and a natural potential barrier is developed across a depletion layer, which is approximately 0.5 to 0.7 volts for silicon diodes and approximately 0.3 volts for germanium diodes. When a junction diode is forward biased, the thickness of the depletion region reduces and the diode acts like a short circuit, allowing full current to flow. When a junction diode is reverse biased, the thickness of the depletion region increases and the diode acts like an open circuit, blocking any current flow, or only a very small leakage current. Here we see two diagrams, one for an ideal diode, current versus voltage, one for a real diode, current versus voltage. When an ideal diode is forward biased, it behaves like a short circuit. As soon as the voltage becomes positive, current flows. In the opposite direction, when it is reverse biased, no current flows. It behaves like an open circuit. A real diode, when it is forward biased, no current will flow until the voltage exceeds a threshold, here shown as 0.7 volts. So at forward biasing, when the voltage exceeds this threshold voltage, then current will begin to flow. And when voltage is reduced from that 0.7 voltage in the opposite direction, reverse biased, no current will flow unless this reverse bias voltage becomes exceedingly large. What is a signal diode? The signal diode is a small, nonlinear, two-terminal semiconductor device which conducts current when forward biased and blocks current when reverse biased. The most widely used signal diode is the 1N4148 or 1N914. Small signal diodes have lower current and power ratings, usually 150 milliamps, 500 milliwatts, compared to rectifier diodes, but they function better in small current, high frequency applications or in clipping and switching applications that deal with short duration pulse waveforms. Here we see the signal diode forward biased with the 0.7 volt threshold. It behaves like a short circuit. Here we see it reverse biased, behaving like an open circuit. The 1N4148 signal diode is a general purpose diode. It has a forward voltage drop of 0.72 volts with a 300 milliamp maximum forward current rating. Here you see the physical size of the diode. The 1N4001 is a rectifier or power diode. It has a higher maximum current rating, 1 amp, and a larger forward voltage, 1.1 volts. Here is another diagram showing the current voltage characteristic of the diode. Here is a diagram showing the P-type and N-type materials that comprise the diode, with the anode and cathode. The anode being plus, cathode being minus. We see the bar in the schematic corresponds to the dark circle on the actual device. That's how we identify anode and cathode. When it is forward biased, we get a voltage drop of 0.3 volts for germanium, 0.7 volts for silicon, a threshold voltage before it will actually start to conduct current. And in the reverse bias direction, there is only leakage current until the voltage gets exceedingly large in the negative direction. Signal diodes are manufactured in a range of voltage and current ratings. The most important characteristics are maximum forward current. This is the maximum forward current allowed to flow through the device. When the diode is conducting in the forward bias condition, it has a small resistance across the PN junction. Power is dissipated across the junction in the form of heat. Exceeding the maximum current will cause more heat to be generated across the junction, and the diode will fail due to thermal overload. The 1N4148 signal diode has a maximum current rating of 150 milliamps with a power dissipation of 500 milliwatts at 25 degrees centigrade. A resistor should be used in series with the diode to limit the forward current. Maximum reverse voltage. This is the maximum allowable reverse operating voltage that can be applied across the diode without reverse breakdown. Typical values range from a few volts to thousands of volts. This parameter is used mainly for diodes in AC rectifier circuits with reference to the amplitude of the voltage, where the sinusoidal waveform changes from a positive to a negative value on each cycle. Total power dissipation. This is the maximum possible power dissipation of the diode when it is forward biased, that is, conducting. When current flows through the signal diode, there is some resistance to the flow of current, resulting in power being dissipated in the form of heat. As small signal diodes are nonlinear devices, the resistance of the PN junction is not constant. It is a dynamic property. We cannot use Ohm's law to define the power in terms of current and resistance or voltage and resistance as we can for resistors. Then to find the power dissipated by the diode, multiply the voltage drop across it times the current flowing through it. Signal diodes in series. Diodes are connected in series to provide a constant DC voltage across the diode combination. The output voltage across the diodes remains constant despite changes in the load current drawn from the series combination or changes in the DC power supply voltage that feeds them. Signal diodes can be used in series and in parallel with a load resistance. Here we have 3 diodes in series. The voltage drop across each diode is 0.7 volts. The circuit is supplied with 10 volts. The voltage to the resistive load is 10 minus 2.1 volts or 7.9 volts. Here we have 3 diodes in series and together in parallel with the resistive load. The voltage drop across the 3 diodes is 2.1 volts. That's the voltage supplied to the resistive load. The 10 volt supply minus the 2.1 volts is then the voltage drop across RD, resulting in a current that is equal to 10 volts minus 2.1 volts divided by that resistance. RD is used to prevent excessive current flowing through the diodes if the load is removed. The freewheeling diode. Signal diodes can also be used in a variety of clamping, protection, and wave shaping circuits. The most common form of clamping diode uses a diode connected in parallel with a coil or inductive load to prevent damage to the switching circuit by suppressing the voltage spikes and/or transients that are generated when the load is suddenly turned off. This type of diode is generally known as a freewheel diode. The freewheel diode is used to protect solid-state switches from damage by reverse battery protection, as well as protection from highly inductive loads, such as relay coils or motors. Here we see protection against an inductive load and the protection of the semiconductor MOSFET. Modern fast-switching power semiconductor devices require fast-switching diodes, such as freewheeling diodes, to protect them from inductive loads, such as motor coils or relay windings. Every time the switching device is turned on, the freewheel diode changes from a conducting state to a blocking state as it becomes reverse biased. However, when the device rapidly turns off, the diode becomes forward biased, and the collapse of the energy stored in the coil causes a current to flow through the freewheel diode. Without the protection of the freewheel diode, rapidly changing currents would cause a high voltage spike or transient to flow around the circuit, possibly damaging the switching device. Power diodes and rectifiers. Power diodes are semiconductor PN junctions capable of passing large currents at high voltage values for use in rectifier circuits. The conversion of an alternating voltage into a continuous voltage is called rectification. Small signal diodes can be used as rectifiers in low power, low current, it's less than 1 amp, rectifiers. But where larger forward bias currents or higher reverse bias blocking voltages are involved, the PN junction of a small signal diode would eventually overheat and melt, so larger, more robust power diodes are used instead. The power semiconductor diode, known simply as the power diode, has a much larger PN junction area compared to the smaller signal diode, resulting in a high forward current capability of up to several hundred amps and a reverse blocking voltage of up to several thousand volts. Since the power diode has a large PN junction, it is not suitable for high-frequency applications above 1 megahertz. Special, expensive high-frequency, high-current diodes are available. For high-frequency rectifier applications, Schottky diodes are generally used because of their short reverse recovery time and low voltage drop in the forward bias condition. Power diodes are designed to have a forward on resistance of fractions of an ohm, while their reverse blocking resistance is in the megahertz range. If an alternating voltage is applied across a power diode during the positive half cycle, the diode will conduct passing current, and during the negative half cycle, the diode will not conduct, blocking the flow of current. Then conduction through the power diode only occurs during the positive half cycle and is therefore unidirectional. Here we see a power diode rectifier, or sinusoidal waveform, and our diode. Current only flows through the diode during the positive half cycle. There is no negative half cycle. We call this the rectified output waveform. Here is a half-wave rectifier circuit. Our voltage supply, diode, load resistance. Here is the AC input waveform. The resultant output waveform is shown here. The diode only conducts during the positive portion of the AC input waveform. The value of the irregular voltage is equal to an equivalent DC voltage of 0.318 Vmax. Here is the equivalent DC voltage of this waveform. The DC voltage is equal to Vmax over pi, which is 0.318 of Vmax. It's also equal to 0.45 of Vrms, root mean square, where Vrms is 0.707 of Vmax. The variation of the rectified output waveform between the on and off condition produces a waveform which has large amounts of ripple. The resultant DC ripple has a frequency that is equal to that of the AC supply frequency. When rectifying an alternating voltage, we often wish to produce a steady and continuous DC voltage free from any voltage variations or ripple. One way of doing this is to connect a large value capacitor, a smoothing capacitor, across the output voltage terminals in parallel with the load resistor. And we see that smoothing capacitor here. The output waveform without the capacitor is shown by the dashed line. The output waveform with the capacitor is shown by the solid green line, where you see the capacitor charging and then discharging, and charging and then discharging. In practice, the half-wave rectifier is used most often in low-power applications. The output amplitude is less than the input amplitude. There is no output during the negative half cycle, so half the power is wasted, and the output is pulsed DC, resulting in excessive ripple. To overcome these disadvantages, several power diodes are connected to produce a full-wave rectifier. Like the half-wave circuit, a full-wave rectifier circuit produces an output voltage or current which is purely DC. Full-wave rectifiers have fundamental advantages over the half-wave rectifier. The average DC output voltage is higher, and the output has much less ripple, hence a smoother output waveform. Here is a full-wave rectifier with two diodes and your load resistance. Current flows here when this diode conducts. Current flows here when this diode conducts. Here we see a full-wave rectifier. Our AC input, two secondary windings, two diodes, current flowing in the same direction through the load resistance during both half cycles. The full-wave rectifier circuit consists of these two power diodes, D1 and D2, connected to a single load resistance, RL, with each diode taking turn to supply current to the load. When point A of the transformer is positive with respect to point C, diode D1 conducts in the forward direction as indicated by the arrow. When point B is positive in the negative half of the cycle with respect to point C, diode D2 conducts in the forward direction as shown by the arrow. The current flowing through the resistor RL is in the same direction for both half cycles. The DC voltage is now equal to 2 times Vmax divided by pi, or 0.637 Vmax, which equals 0.9 of V RMS. The main disadvantage of the full wave rectifier circuit is that a large transformer for a given power output is required with two separate but identical secondary windings, making this type of full wave rectifying circuit costly. The main advantage of the bridge circuit below is that it does not require a special center tap transformer. Here is the full wave bridge rectifier with 4 diodes in the form of a bridge circuit. During the positive half cycle, D4 and D3 conduct. During the negative half cycle, D1 and D2 conduct. And there is our load resistance. And in both cases, the current flowing through the load resistance is in the same direction. The full wave bridge rectifier gives a mean DC value equal to 0.637 Vmax with less superimposed ripple. The output waveform frequency is twice that of the input supply frequency. A smoothing or reservoir capacitor, shown here, connected in parallel with the load across the output of the full wave bridge rectifier circuit, reduces the AC variation of the rectified output and increases the average DC output level even higher, as the capacitor acts like a storage device. The voltage ripple magnitude equals I load, which is the DC load current in amps, divided by the frequency, F, which is twice the input frequency in hertz, divided by the capacitance value, C, in farads. And this gives us amperes divided by hertz divided by farads, which is volts. So we see here our full wave bridge rectifier with the 4 diodes, smoothing capacitor, load resistance. The waveform without the capacitor is shown by the dashed line, and we see the waveform with the capacitor is shown here with a greatly reduced ripple. Let's perform a hardware demonstration. Let's input a sine wave that is 50 hertz, 50 cycles per second, 5 volts peak to peak. Here is the bridge circuit with 4 diodes, D1, D2, D3, D4. My smoothing capacitor is a 232 microfarad capacitor. My load resistance is a 995 ohm load resistor. What I expect to see is a waveform with a capacitor that looks like this, with very little ripple. This is the resultant output waveform. On the oscilloscope, I show my input signal, 50 hertz, Vmax is 5 volts. The sine wave goes from plus 5 volts to minus 5 volts. We see the frequency here, 50 hertz, peak to peak, 10.5 volts. This is the output without the smoothing capacitor. We see the frequency is 100 hertz, twice the 50 hertz signal of the sine wave. The peak-to-peak voltage is 3.8 volts, and we see that here in our measurements on the oscilloscope. Here is the output on the oscilloscope with the smoothing capacitor. Note that the frequency is 100 hertz. The peak-to-peak voltage is 180 millivolts. The average voltage is 2.98 volts. I calculate the ripple voltage to be slightly different, 129 millivolts. The discrepancy needs to be investigated. The Zener diode. The Zener diode is used to intentionally conduct reverse current. It has a very precise breakdown voltage called the Zener voltage. When enough current runs in reverse, the voltage drop holds steady at the breakdown voltage. Here we see the Zener voltage, a known reference voltage to be 3.3 volts. And note the representation of the Zener diode. Unlike a conventional diode that blocks any flow of current through itself when reverse biased, that is, the cathode becomes more positive than the anode, as soon as the reverse voltage reaches a predetermined value, the Zener diode begins to conduct in the reverse direction. The current now flowing through the Zener diode increases dramatically to the maximum circuit value, which is usually limited by a series resistor. And once achieved, this reverse saturation current remains constant over a wide range of reverse voltages. Here we see a graph of the Zener diode current voltage characteristics. The Zener voltage can range from less than 1 volt to a few hundred volts. The point at which the Zener voltage triggers the current to flow through the diode can be very accurately controlled to less than 1% tolerance in the doping stage of the diode semiconductor construction. Here we see the symbol for the Zener diode. There's the anode and there's the cathode. When we forward bias the Zener diode, it behaves like a normal diode. The knee voltage, where current starts to flow, is between 0.3 and 0.7 volts. Here is the Zener breakdown region. When we get to a Zener voltage, current begins to flow, and the voltage stays constant. This is the constant Zener voltage. The Zener diode is used in its reverse bias mode. That is, the diode anode connects to the negative supply. From the current voltage characteristics curve, we see that the Zener diode has a region in its reverse bias characteristics of almost a constant negative voltage, regardless of the value of the current flowing through the diode. This voltage remains almost constant, even with large changes in current, providing the Zener diode current remains between the breakdown current, Iz min, and its maximum current rating, Iz max. This ability of the Zener diode to control itself can be used to great effect to regulate or stabilize a voltage source against supply or load variations. The fact that the voltage across the diode in the breakdown region is almost constant turns out to be an important characteristic of the Zener diode, as it can be used in the simplest types of voltage regulator applications. The function of a voltage regulator is to provide a constant output voltage to a load connected in parallel with it, despite the ripples in the supply voltage or variations in the load current. A Zener diode will continue to regulate its voltage until the diode holding current falls below the minimum Iz min value in the reverse breakdown region. Here is a Zener diode regulator. Zener diodes can be used to produce a stabilized voltage output with low ripple under varying load current conditions. By passing a small current through the diode from a voltage source via a suitable current limiting resistor, R sub S, as shown here, the Zener diode will conduct sufficient current to maintain a voltage drop of V out. V out is shown here, it's equal to the Zener voltage. The DC output voltage from the half-wave or full-wave rectifiers contains ripple superimposed onto the DC voltage. And as the load value changes, so too does the average output voltage. By connecting a simple Zener stabilizer circuit, as shown, across the output of the rectifier, a more stable output voltage can be produced, as this voltage across the load resistor is always equal to Vz, provided the supply voltage is greater than Vz. And in this case, for the Zener diode, the cathode is connected to the positive rail. That is, it is reverse biased. Resistor R sub S is selected to limit the maximum current flowing in the circuit. Care must be taken when selecting this value so that the maximum power rating is not exceeded under a no load or high impedance condition. As well as producing a single stabilized voltage output, Zener diodes can also be connected in series, as shown here, along with normal silicon signal diodes, as we have right here. And this is used to produce a variety of different reference voltage output values. The values of the individual Zener diodes can be chosen to suit the application, while the silicon diode will always drop about 0.6 to 0.7 volts in the forward bias condition. The supply voltage Vin must be higher than the largest output reference voltage. And we see that combination right here. Zener diode clipping circuits. Diode clipping and clamping circuits are circuits used to shape or modify an input AC waveform, or any sinusoid, producing a differently shaped output waveform depending on the circuit arrangement. Diode clipper circuits are also called limiters because they limit or clip off the positive or negative part of an input AC signal. As Zener clipper circuits limit or cut off part of the waveform across them, they are mainly used for circuit protection or in waveform shaping circuits. Here we see a sinusoidal waveform, our Zener diode, and the clipping that happens at the Zener diode voltage. This is a single Zener diode clipping circuit. Here we have two Zener diodes, a double Zener diode clipping circuit, and we see the clipping happening at both the top and bottom of the sinusoidal waveform. If we wanted to clip an output waveform at plus 7.5 volts, we would use a 7.5 volt Zener diode. If the output waveform tries to exceed the 7.5 volt limit, the Zener diode will clip off the excess voltage from the input, producing a waveform with a flat top while keeping the output constant at plus 7.5 volts. Note that in the forward bias condition, a Zener diode is still a diode, and when the AC waveform output goes negative, below minus 0.7 volts, the Zener diode turns on like any normal silicon diode would and clips the output at minus 0.7 volts. And we see that here. The back-to-back connected Zener diodes can be used as an AC regulator. Using this arrangement, we can clip the waveform between a positive value of 8.2 volts and a negative value of minus 8.2 volts for a 7.5 volt Zener diode. If we wanted to clip an output waveform between two different minimum and maximum values, we would use two differently rated Zener diodes. This type of clipper configuration is common for protecting an electronic circuit from overvoltage. The two Zener diodes are generally placed across the power supply input terminals, and during normal operation, one of the Zener diodes is off, and the diodes have little or no effect. However, if the input voltage waveform exceeds its limit, then the Zener diodes turn on and clip the input to protect the circuit. And we see the two Zener diodes the sinusoidal waveform, and the clipped output waveform. The Schottky diode is a metal semiconductor diode with a low forward voltage drop and a very fast switching speed. Here we see the current voltage characteristic curve, and for a normal silicon p-n junction diode, the knee voltage is about 0.7 volts. For the Schottky metal semiconductor junction diode, the knee voltage is about 0.4 volts. The general shape of the metal semiconductor Schottky diode, the current voltage characteristics, is very similar to that of a standard p-n junction diode, except the corner or knee voltage at which the MS junction diode starts to conduct is much lower at around 0.4 volts. Due to this lower value, the forward current of a silicon Schottky diode can be many times larger than that of a typical p-n junction diode, depending on the metal electrode used. A smaller forward voltage drop for a given diode current will produce lower forward power dissipation in the form of heat across the junction. This lower power loss makes the Schottky diode a good choice in low voltage and high current applications, such as solar photovoltaic panels, where the forward voltage drop across a standard p-n junction diode would produce an excessive heating effect. However, it must be noted that the reverse leakage current for a Schottky diode is generally much larger than for a p-n junction diode. Here is the Schottky diode construction and symbol. Here is a symbol. Here is the anode, the cathode. The metal semiconductor MS junction is shown here, which is very small, between the metal and the N-type silicon. The Schottky diode has a very rapid response to changes in bias and demonstrates the characteristics of a rectifying diode. For practical silicon junction diodes, this knee voltage can be anywhere between 0.6 and 0.9 volts depending upon how it was doped during manufacture and whether the device is a small signal diode or a much larger rectifying diode. The knee voltage for a standard germanium diode is, however, much lower at approximately 0.3 volts, making it more suited to small signal applications. But there is another type of rectifying diode which has a small knee voltage as well as a fast switching speed, which we now know is called a Schottky diode. Schottky diodes can be used in many of the same applications as conventional p-n junction diodes, but especially in digital logic, renewable energy, and solar panel applications. Unlike a conventional p-n junction diode, which is formed from a piece of p-type material and a piece of n-type material, Schottky diodes are constructed using a metal electrode bonded to a n-type semiconductor. Since they are constructed using a metal compound on one side of their junction and doped silicon on the other side, the Schottky diode has no depletion layer, and they are classified as unipolar devices, unlike typical p-n junction diodes, which are bipolar devices. In a Schottky diode, a lightly doped n-type silicon semiconductor is joined with a metal electrode to produce a metal semiconductor junction. The width of the MS junction will depend on the type of metal and semiconductor material used, but when forward biased, electrons move from the n-type material to the metal electrode, allowing current to flow. Thus, current through the Schottky diode is the result of the drift of majority carriers. Since there is no p-type semiconductor material and therefore no minority carriers, holes, when reverse biased, the diode conduction stops very quickly and changes to blocking current flow as for a conventional p-n junction diode. Thus, for a Schottky diode, there is a very rapid response to changes in bias as it demonstrates the characteristics of a rectifying diode. Light-emitting diodes, or LEDs. The LED, light-emitting diode, is a semiconductor device that converts electrical energy into light energy when it is forward biased. It has similar electrical characteristics to a p-n junction diode. It passes current in the forward direction, but blocks current in the reverse direction. Light-emitting diodes are made from semiconductor compounds mixed in different ratios to produce a distinct wavelength of colored light or infrared light when forward biased. The p-n junction of a LED is surrounded by a transparent, hard plastic shell which protects the LED from both vibration and shock. All LEDs are manufactured with two legs protruding from the bottom of the body. The cathode is identified by either a notch or flat spot on the body or by the leg length, with the cathode lead being shorter than the anode lead. The LED generates cold light, as most of the generated energy radiates away within the visible spectrum. LEDs provide longer life than normal light sources. Like conventional p-n junction diodes, light-emitting diodes are current-dependent devices with its forward voltage drop, V sub F, dependent on the semiconductor compound and on the forward biased LED current. Most common LEDs require a forward operating voltage of between 1.2 to 3.6 volts with a forward current rating of 10 to 30 milliamps, with 12 to 20 milliamps being the most common range. Here's a table showing typical LED characteristics: the semiconductor material, the wavelength, color, and the forward voltage at 20 milliamps. Here is the light-emitting diode current voltage characteristic curves for infrared, red, amber, yellow, green, blue, and white LEDs. This is the forward voltage. This is the forward current in milliamps. Here is the conventional current flow through the diode, the anode and the cathode, and the notch showing the shorter lead, the cathode, and the longer lead being the anode. So this is the LED and its current voltage characteristics. Before a light-emitting diode can emit any form of light, it needs a current to flow through it, as it is a current-dependent device with light output intensity being directly proportional to the forward current flowing through the LED. As the LED is to be connected in a forward bias condition across a power supply, it should be current limited using a series resistor to protect it from excessive current flow. Never connect an LED directly to a battery or power supply, as it will be destroyed almost instantly because too much current will pass through and burn it out. Each LED has its own forward voltage drop across the p-n junction, and this parameter, determined by the semiconductor material used, is the forward voltage drop for a specified amount of forward conduction current, typically for a forward current of 20 milliamps, as we saw in the table. In most cases, LEDs are operated from a low voltage DC supply with a series resistor used to limit the forward current to a safe value from 5 milliamps for a simple LED indicator to 30 milliamps or more when a high brightness light output is needed. Here is a LED current limiting series resistor. R sub S. Here is the LED with the forward voltage drop. Here is our supply voltage. And we can size the resistor by specifying the amount of current, knowing the supply voltage, and the voltage drop across the LED. Series LEDs. LEDs can be connected in series, as we show here, to increase the number required or to increase the light level when used in displays. As with series resistors, LEDs connected in series all have the same forward current flowing through them. As all the LEDs connected in series pass the same current, it is generally best if they are all the same color or type. So we see the same current flowing all through all of the LEDs. The voltage drop across all of the LEDs is 3 times the voltage drop across one of the LEDs. And we size the resistor using our same formula for supply voltage minus the voltage drop across the LEDs divided by the desired current, and that will then size the resistor, the current limiting resistor, for us. LED light intensity using pulse width modulation. We have a module in this series on pulse width modulation. A pulse width modulated or PWM current with a short duty cycle allows the diode current, and therefore the output light intensity, to be increased significantly during the actual pulses while keeping the LED average current level and power dissipation within safe limits. This on-off flashing condition does not affect what is seen by the human eye, as it fills in the gaps between the on and off light pulses, providing the pulse frequency is high enough, making it appear as a continuous light output. Pulses at a frequency of 100 Hertz or more actually appear brighter to the eye than a continuous light of the same average intensity. Here is our LED with our current limiting resistor, and here we have our pulse width modulated signal. We see the period and we see the duty cycle. A larger duty cycle will produce a wide pulse, bright. Narrow duty cycle or small duty cycle will produce a narrow pulse, a dim light. This concludes the module on diodes. You've learned about the variety of diodes that are available, as well as the applications in which they are used. And you've seen how the diode is the most basic active electrical component, essential for mechatronics. Thank you for your attention.